Good morning, everyone. I'm very happy to have Avi today to talk about expanding groups.
Hi. Okay. It's a talk, the version of a talk I gave at a conference at Rizwan and Weizmann on many high-dimensional expanders about a couple of years ago, a year ago, I don't remember. And I gave it in an hour, and it was only group theory, so many group theories in the audience, and they told me it was too fast. So I tried to give it in 2 hours, and I had obviously the material. So it's on slide because I make everything on slide, so it will be available at my website. That's everything. If I gave it on the board, it would probably take 4 hours just to write all the references down. So, apropos references, there are lots of them that will be missing. I mean, there'll be plenty of material here, and obviously things I will not mention. Anyway, I want to talk about expansion in groups. This is a 50-year activity. The main question we'll deal with is which groups and for which generating sets the Cayley graphs suggest are expanding. Just for everybody's, one slide on expanders, the obvious thing, we will look at undirected graphs. They are deregularizing of DS fixed, the degree, but actually we think about a family of graphs of size n and going to infinity. And the amazing thing about expanders is that they have, you can define them from lots of points of view, combinatorially or geometrically. You can think about high isoperimetry, no small cuts in the graph, high connectivity. From a probabilistic point of view, you can think about the natural random walk on the graph, and you want to say that it converges very fast. And algebraically, you can study the adjacency matrix and look at the second eigenvalue, say that it's small. And what is amazing and what makes this expander sort of a fundamental object is that all these points of view are really equivalent, that there are quantitative connections between these parameters. That's a long series of works that understand that. So we will look mainly at the algebraic definition here, namely second eigenvalue. And one convenient way, I'm sure you've all seen this, but stop me with anything and I can use the board and write things or elaborate some things if you want. One way to say what the second eigenvalue of this graph is, this expansion parameter, is you look at the random walk matrix, which is a stochastic matrix, has eigenvalue 1. That's a trivial eigenvalue, and the eigenvector is a constant function. If you subtract the all ones matrix, namely the random walk on the complete graph, from it normalized, and look at the norm, this is the same as looking at the second eigenvalue. That will give you the parameter we care about. And this parameter is always between 0 and 1, and we call a graph an expander if it's, this value is bounded away from 1. I can write 0.999, or can write 1 minus epsilon for fixed epsilon for this family of graphs with going n. And
small second eigenvalue in absolute value.
In absolute value, exactly. That's the expansion parameter we have. And it's the same thing with what's called the spectral gap is bounded away from 0, 1 minus this number. So that's an expander.
To bipartiteness and so on.
Yeah, so it will not be bipartite. It's bipartite at self-group. You never worry about this here, at least. So we care about Cayley graphs, so here are some examples. These are examples actually of non-expanders, but these are Cayley graphs just to establish notation. If I have a finite group and I have a symmetric subset, symmetric means closed under taking inverse, because I want undirected graphs, then here's the Cayley graph of the cycle with plus minus 1 generators. There's the Cayley graph of the cube with the unit vectors that generate, then we know that these are poor expanders. Here's a good expander. Here's I stole a picture from this paper Now I don't even remember the author. In most cases, I write them down. So what is this picture of? This is a case P equals 3 of the Cayley graph of the group SL to P, so 2 by 2 matrices with answers modulo P. And with this pair of generators and their inverses, two matrices below. Okay, and this, as we'll see in many ways, is very good, are very good. So the question is which G and which S give us expanding groups, and more to the point, that's a survey. How do we prove that? How do we prove that these are expanded? How do we bound the second eigenvalue of the random walk matrices on such problems? So I have to do, this is more or less the method we know. We know a little more than I wrote here, but I'll go through most of them in some detail, starting with this mother group approach of starting with Margulis, property T, and understanding some Cayley expanders, in particular this approach that gave us the famous Ramanujan graphs and give us most of the examples we have of high-dimensional expanders today. The zigzag product, which I'll talk about at the end, which was designed as a combinatorial alternative to the algebraic approach, but turns out to be very related to algebra and groups, and we'll see how to get some non-simple groups as expanders from this method. Of course, this has other implications that maybe I'll mention later in more detail. I will not talk about this amazing method, namely the method of lifting, starting with Bilwen lineal and leading to Marcus Spielmann Srivastava of building expanders iteratively like zigzag product, but different kinds of iterations solve famous problems in math, like Callison single conjecture. Should mention that lots of ways in which we try to prove that Cayley graphs expand lead to understanding in other questions. Anyway, then I'll talk about bounded generation methods introduced by Shalom that eventually led to showing that essentially all simple groups expand. So this major result. So we'll talk about this. Then I'll survey briefly, but in some detail, the method that is based on arithmetic combinatorics. So you see, we borrow from lots and lots of areas in this attempts to prove expansion. You may wonder, many people ask this question, you have a construction, you have a proof, why do you need another? Why do you need? It's often it's the same groups for which you prove expansion by different parameters, and the answer is obvious. We want, I think in math in general, we want different proofs of the same theorem. It's always good. So here, arithmetic combinatorics, how is it related to groups at all? You think about APs and primes or something like this. How is this related? It's related. We'll see how. And finally, the method of Gromov of building, expanders randomly, but infinite expanders. So it's not obvious. It's not obvious even what it means, but again, something that's related to foundational questions in topology. So I will expand on most of these. But before that, I want to give you like a crash course on finite group representation theory. I do just the minimal that you will find, so many of you know. You'll find the first chapter of any book on finite groups and their representation. It's extremely convenient. It's extremely convenient to know this and to use it. It's a very powerful language. It's a very beautiful theory with lots of things I'm not going to talk. So we start with groups. So we'll fix a group G of size n. Almost all the time I work over the field, the complex field, but somewhere we need fields of positive characteristic. And the whole theory I'll tell you about in these slides, in these 3 slides, remains the same, exactly the same, as long as the characteristic of the field does not divide the size of the field. When it does, it's a much more elaborate theory in group representation that I don't need and I will not get into. Anyway, everything remains the same. So what's going on? Right? Groups are a nonlinear object. You want to understand it. We don't understand anything nonlinear in mathematics. We have to linearize. How do we linearize it? Well, any objects, you have a group, a field, a manifold, a variety, all sorts of crazy objects that you want to understand in mathematics. To linearize is very simple. You look at all functions of it, on it, into some field. That's already a vector space, and that's the beginning. Okay. So that's what we do with groups, and that's how group representation starts. So to linearize, one way is to look at matrices. How do groups relate to matrices? Groups act on themselves by multiplication. So groups are actually permutation groups. In an obvious way, if you have an element Z in the group, you can draw a permutation matrix with group elements in the rows and the columns, and you can see where Z moves every element, right? So that's this is this permutation representation or simple matrix representation. So it's a homomorphism from the group, right? For every element, you map it to a matrix. There's a mapping into matrices which are n by n, and whenever I have a red arrow, it's a homomorphism. Okay, so we have a homomorphism to this matrix group. We can think of the group as a matrix group. And now we do what I said. We look at not just these delta functions, the functions on the group, which are just the elements, but any linear combination of them, all functions on the group. Okay, all functions on the group. I forgot to say, without loss of generality, this map only gives unitary matrices. The image is always unitary matrices, and that's why we'll explain. It's easy to see that all eigenvalues have to be 1 in absolute value, because when you raise your matrix to the nth power, you get the identity, right? All elements to the nth power are 1. So, I will not say it, but they are all unitary. And now we extend to the whole group. So this is what's called the group algebra. What is the group algebra? Is a collection of all functions on the group, or in other words, all linear combinations of group elements with this field you have, in this case, complex numbers. And you can also explicitly say what is this representation. So R is called the regular representation. What is this matrix for an arbitrary function? Well, it's a linear combination of these permutation matrices. That's one way of seeing it. Another way of seeing it is a matrix in which in the xy coordinate you put f of xy inverse. This is what you did in the case of a single element, and that's in general. So it's a matrix in which in every row in every column you have the function f permuted in some way. Okay, and we'll need it later. So very structured. Very structured collection of matrices. That's a regular representation, and it's an algebra, right? I mean, you can add 2 matrices and get another matrix. You just add as a function. You can multiply 2 matrices like matrix multiplication, and you get the representation of the convolution. So that's very convenient in itself. We'll use it later. And moreover, why do we need this group algebra? Because the object we are going to study, adjacency matrix and random walk matrices of this group, are elements of this algebra, right? And if you take any symmetric group, any symmetric element, it's of size k, or size k, we add these values, right? What do we get? We get the adjacency matrix Everybody sees that. We just add the permutation matrices. And if we just want to look at the random walk matrix, so we just divide by k. So that will be my random walk matrix. So random walk matrix is an element of the algebra, so it will be very useful for us. And of course, this homomorphism is linear, but it goes under addition. So I can write R of the average, this function, which is the average of my generator, and sometimes I'll summarize this like this, R of S. So this is what we want to understand the normal for the second eigenvalue. Okay, now that's our task. We seek upper bound on lambda of R of S for a variety of S. Questions?
Wait, obviously, when you're writing R of S there, S is the function, or could you go back?
S, yeah.
S is the function which multiplies by S.
Yeah, S is a function with 1 over k on each element of it. Yeah, exactly. So now we talk about the irreducible representations. So I'll remind you something you know, and you'll see that it's the same. What you know is Fourier analysis. So Fourier analysis is the representation theory of abelian groups. Here we have the group algebra, and the Fourier transform says that there are, these n magical functions, the group is of size n, and magical functions, homomorphisms, form the group to the unit circle, right? And the unitary transformation that diagonalizes everything in the group algebra. Right? This is what the Fourier transform does. It diagonalizes all the matrices in the group algebra, which is fantastic, right? Because when you have diagonal things, you can study their eigenvalues just by inspection. So, for example, in abelian groups, so some of you are used to seeing, I look at the representations of a function. Sometimes people use f hat of xi instead of chi instead of chi of f. But, this is what you are familiar with. And in this case, so for abelian group, when we want the second eigenvalue, is simply the value of any character except the trivial one. The trivial character sends all group elements to 1. And I said this corresponds to eigenvector, which is a constant function, which we don't care about. So all the others tell you, the largest of them is the second eigenvalue for this generating set S. Some of you are familiar with this, if this maximum is epsilon, and we are over the Boolean cube, we call this an epsilon bias set. It's a bound on the eigenvalue. So what happens in general groups G? You have the same, you are trying to diagonalize the group algebra as much as possible. That's what you are trying to do. And if you do it as much as you can, you get this. You have still a unitary change of basis like before, like in the Fourier transform. And you, instead of getting, n parts, you get some t parts, t representation. So these are again homomorphisms, like the character. But now to larger matrices, you cannot avoid it because your group is not commutative in general. And this is a unique decomposition, such as when you change the basis, you get diagonals. But what do you find in the diagonal? On the diagonal, you always find, maybe I have this pointer. Yeah. You always find the trivial representation, like the trivial character. You can always send all group elements to 1. That's a one-dimensional character. But in general, there'll be, blocks of some sizes, d sub I for various I along the diagonal. That's what you get. But so I mentioned this, the trivial representation. Another thing I want to mention will be used, is very important for studying eigenvalues, is eigenvalue multiplicity. This is, if you have any representation appearing, and it has dimension d sub I, it will appear, di copies of it will appear. Okay, that is needed. We'll see in a second some explanation to this. but multiplicity of this, of course, implies multiplicity of eigenvalues, and that will be useful. And so the characters correspond to reducible representations in general. This transformation is, the analog of this analog. And the bound of the eigenvalue changes from being, we are always interested in the norm, right? In the norm of the matrices up to, except for the trivial representation. It's the same, exactly the same, right? We look at the maximum norm of any one of these blocks, except the trivial one. This will give us the second eigenvalue. So you see that this theory helps us get into the value we want, the second eigenvalue. One way to summarize what I showed you and a little more is the following theorem of Mashke. Of course, this is 1898. Is that this gives you a decomposition of the group algebra into a direct sum of full matrix algebras. Okay, the group algebra has, dimension n, right? Even though it's n by n matrices, so it's not full algebra. But this decomposition makes it so that you have full matrix algebras, and the one coming from the ith representation appears di time. One way so full matrix algebras are easy to study. That's another convenient feature of this decomposition. You can infer from this, I'll tell you just high level, this formula, which I'm sure some of you have seen. Something you know about the dimensions of this representation of this is that the sum of the di squared is n, the size of the group. One way to see it is that counting parameters, functions on the group have dimension n, right? And how many parameters do you see in this picture? If each row I give us di squared parameters, full matrix algebra di by di. Right, so you get di squared. So the number of parameters, the dimensions have to match. That's one way to see it. Another way to see it, or to see why you need these copies, if n is a sum of di squared, then you really want, di times di in the matrix, so that the length of the matrix will be what it should. Anyway, what is, absolutely fantastic about this is that this is all you need to know for anything you do with a group. Okay, what do I mean? If you have any other representation, any other homomorphism on your group to some matrix algebra, anything, any size, and just a homomorphism, then it decomposes to the same prime factor. So you think of the irreducible representations of a group as the prime components, and any other homomorphism will be some direct sum of the same T irreducible representation with some multiplicity. Okay? So in particular, what does it mean? It means that if we want to study, this is what we want to study as a basic thing about the group, the Cayley graph of the group. But if we have a bound for this, then I want to say, well, you have a bound for other representations. So this is what I wrote before, and what it means that, the regular representation tells you all you want to know about any other representation. Some of the spectrum of the regular representation capture the spectrum of any other representation. So I want to give you some examples where this is used in expansion. So, particular for any representation, if you want the bound on the second eigenvalue, I'll give you examples so you know you've seen it. Then you can use it, you can definitely upper bound it by what happens in the regular representation, because these are all representations, they appear there. One place is when you have an action of your group on a set, then every group element is mapped to a permutation of the set, so you get a subgroup of the symmetric group. And these are exactly what's called Schreier graphs of groups. So you're seeing group graphs of actions. In fact, every regular group is a Schreier graph of some group, but we will not talk about Schreier graphs. In this talk, we'll talk about Cayley graphs. There's a lot, it's very powerful for studying Cayley graphs because what the other example of getting a representation is simply when you have some normal subgroup of your group and you look at the quotient. In this case, the quotient is another group and quotients will appear a lot. You have a quotient group and you have a natural homomorphism from the group to the quotient. You simply send elements to their quotients, right? So then what you get is, another Cayley graph on this subgroup with the same generators. The generators mapped to their quotients. So we can study, we get immediately upper bounds on second eigenvalue of these representations, these quotient groups, if we have access to bounds on the large group. And we have a lot of this, and what we'll start with is this property T, which are is usually defined differently, but let me tell you what property is for this talk. You have an infinite group. I'll talk mostly about finite groups, but we'll need a little bit of infinite. We have an infinite group. It still has irreducible representations, but some of them are infinite dimensional. But anyway, let's say it's finitely generated by some symmetric set S. We say that it has property T if, it's an expander basically, right? Its lambda is bounded away from 1 by some fixed epsilon. For infinite groups, this property is independent of the generating set because you can generate it. Yeah, you can see this very, very easy to see. So Kashdan didn't only define this, he actually proved that basic will exist in the second, proved that some natural groups have this property, and that was the beginning of expanders, NK, explicit expanders, NK. Question?
So it's equal to 1 minus epsilon or at most 1?
Yeah, for some epsilon it's equal. Yeah, very good. So it's at most, yeah. At most 1 minus. For epsilon.
So it's the same both for S, don't you?
No, of course. Epsilon may change for different S. Yeah, but it's already for any finite generating S, it's a fixed epsilon.
Does this hold for every representation, or you want this?
Yeah, this is for all representations.
Not just regular.
This is a property T. Later, no. I mean, this is talking about the regular representation of the infinite group. So it talks about all irreducible representation. So you can say it's about the regular representation or its decomposition the same.
So Avi, but this strategy could be quite weak, right? Like in some sense.
Not only weak, sometimes, we'll talk about this, but Hazan proved it. He didn't have any explicit bounds on this epsilon. Yeah, we'll talk about that.
Right. No, I guess what I wanted to say was that, you could actually find an action of G that has much better expansion than G.
Of course, it's just upper bound, but this upper bound is very powerful. If you know something about the group, you know something about all its quotient. And this will be the...
But I think you should say that for finite groups, it's trivial, right?
For finite group, it's trivial.
I mean, because
I can say... If I say, yeah. But for finite groups, we always think about the family of groups, and it's not true.
Yeah, I'm saying that there's something about infinite groups that is different from the story you said.
Yeah, you don't need, you're right, you don't need the fixed epsilon, and the group is infinite. But if you think about all its finite quotients, the same epsilon will bound their eigenvalue by this. Yeah, so this is really the beginning of everything. That's it's 50 years or a little more than 50 years. This is what some people call the mother group method for proving expansion on Cayley graphs for fun. Starting with this famous paper of Margulis. This is, people like to tell this story as a positive influence of anti-Semitism in Russia. Pinsker, who famously proved that expanders exist, bounded degree expanders by the probabilistic method, was working with Margulis at this institute. They both couldn't get positions at the university, being Jewish. And so he had a probabilistic construction, asked Margulis whether he has an explicit construction, and Margulis probably thought about this a minute and said yes. Yeah, because he said yes, because it's the end of the talk.
You got into politics.
Yeah. No, it's okay. I need to click on something. So, what's the mother group approach? It's just what we saw before. If we have some discrete group, like an infinite group with a finite generating set, and it is expanding, then all its quotient, in particular its finite quotient, will expand with the same generating set. And which examples do we have? So Margulis appealed to Kasdan property T, and Kasdan proves that, for example, SLD of Z, so these are 3 by 3 or D by D matrices with determinant 1 over the integers, has property T. This has major impact on mathematics. For some, it was probably 17 or something. It has major impact in solving open problems in algebra. But anyway, Margulis realized that you can use it to bound the eigenvalue of the quotient. 2 by 2 was a mystery that was resolved by lots of things in these are elementary things plus a reduction to some black box that some big theorem. So Lubotsky, Philip Sarnak used instead for 2 by 2 matrices. They used the result of Sedberg called the 316 theorem. This group does not have property, but it has a strong enough property, I'll show you in a second. And in particular, in the same paper of LPS, they also, built the famous Ramanujan graphs, and then they appealed to a result of Delin, solving the Weil conjecture, the Ramanujan conjecture, this very important work. And there are many other mother groups. We'll see more later. But I just want to say that we want quotient groups. Yeah, I mean, an infinite group is no good if it doesn't have finite quotients. And not every infinite group has finite quotients. But, you can always do modulo P. Right? If you have the integers, you can always do modulo P. That gives you finite quotients immediately. Because of the property of Kasdan applies to all representations, to the regular representation, you can take any generator. In the Selberg thing, you can take, at least as far as we know, only modular representation, just do modulo P. The other subgroups, and we don't know about them. And here they are in the Ramanujan graphs, for those who know, it will not be important, but these are very specific generators which give you the optimal eigenvalue bound.
So it's any generators of the infinite group, not of the quotient. Any generator, you keep the same generator. Oh,
any generator will, any generator.
They can take any generators of the quotient.
No, you fix the generator. Yes, very good point. I should stress it. You take your generators, any generator of the infinite group, they will do fine for any one of the quotients. Or their image will do fine. You do more period.
So, which paper is the second one? I mean, the one that takes several results?
These two are in LPS. The Lubotsky Philip Sarnak. Yeah, they use the Selberg result.
Operator T only gives you a like positive gap. How
Yeah,
do you get like Ramanujan
Yeah,
equality
we-
from that?
you don't get Ramanujan for property. You get Ramanujan only in this specific case for specific generator.
I see.
Yeah, and this is work. You need the full power of the ring and some more work of the cosine. Anyway,
So Avi,
Yeah.
why is it called property T?
yeah, I don't know.
Because the trivial representation is bounded away from all other representations
isolated, so T is isolated.
in the Feld topology.
Okay,
So it's
so,
just T is isolated. That's
so
all.
T for trivial.
T is for
Yeah,
the
we
trivial
call
representation.
maybe you knew that. Yeah, anyway, we separate the trivial representation as, of course, value one, so we separate all other representations. Yeah, thanks. So we already have an infinite family of expanders from this. Of course, as I said about, here we have actually quantitative bounds. This 316 is sort of an eigenvalue bound. And here it's even better because Ramanujan bound. But from this, we don't get Margulis like for 15 years or so. It looks like there was a gap, no fixed eigenvalue bounds, but people took Margulis's construction, for example, famously Gaber and Galil first, and then Jimbo Maruka, and there are simpler proofs. And you can do a really sort of Fourier analytic proof of the eigenvalue bound, Fourier analysis over the real. It's simple, I taught it in class, takes an hour, it's magic, but yeah. It's elementary, you can get fixed bounds, and there are other ways I'll mention in a second. So we have many sort of finite simple groups, so I remind people, simple groups are the most known simple groups in existence. For finite groups, these are groups that don't have any normal subgroups. I mean, in general, these are groups that have no normal subgroups. They are the building block of all groups, and we'll see with in what way. I want to say that a weaker question, of course, if you have expanded, you have logarithmic diameter, not necessarily the reverse. And this problem, just whether all finite simple groups have generators that give logarithmic diameter, was resolved using different methods earlier. Okay, here's a
bit confused. That part seems trivial, no?
No.
It's finite groups. If I just
Logarithmic diameter.
if I just form words, like I take, like I'm saying, any minimal generating set would be.
Take a billion group, but of course it's not clear, it's not true for the cyclic group, which is also simple. The diameter is n. It's not true. I mean, the diameter bound is not obvious. You have to prove that you grow somehow. I mean,
Permutations, if you take.
for the symmetric group, it's not obvious. Yeah,
Take 1, 2, and 7.
it's not obvious. But this was another method related to the mother group approach in which you can get quantitative bounds and eventually led to our understanding that all non-commutative simple groups expand. I say that almost all these results have an exception. And when you talk about all finite simple groups, you have to remember that we think we know them all, but we know them all modulo this 20,000 page proof of the classification of finite simple groups. So, modulo that. And there are various weird groups that sometimes the methods don't apply to. So Yuda Shalom was the first to introduce this bounded generation method, the simple way to prove property T. I'll say it more generally than he's saying it, but basically what you do is the following. What you want to prove it for a group is it can be an infinite group also, but let's think here is finite groups. You have a collection of subgroups that you can use as generators. Some of you are allowed to use many generators, not a finite number of subgroups. So you want that each of them, they boundedly generate G. This just means that every element of G is a product of one element from each HI, but it can be any element. Okay, so, and there's a constant number of these subgroups. And the other one is that each of them is an expander with some constant generating set, each one of the subgroups. Suppose you know both of these. Then you can combine them. You take the group and you take not all the elements of HI, but just the generating set. This will give you a family of expander. And if you think about this, and you remember, I'll get to Zigzag later, but you remember in the Zigzag paper, there's also a replacement product. This is basically a replacement product, right? If you, yeah, anyway. If it doesn't ring a bell, it doesn't. So using this, and if you have bounds on this generator with subgroups, you can get explicit bounds on the eigenvalue. Then another major result happened.
Avi, can you give what's the example you usually think about with this construction? Shalom.
You can use the SL3, and you can use he's looking at powers, right? He's looking at generated by elementary matrices and all their powers over Z, right? You can write that any matrix is an elementary matrix to some power times another elementary matrix to some power, but you want finite number. You can do that.
Bounded number, I think.
What?
Bounded number.
Bounded, yeah.
Really finite, but like.
It depends on D, yeah. Just depends on D, something like this graph.
But then each one of them is a.
But the exponent may be arbitrary, so it's some elements of it, cyclical. These are all cyclical.
Yeah, but then each HI by itself is just Z.
Is Z, yeah.
And then.
Yeah, so I wrote it here for infinite. So yeah, I'm teasing a little bit. I wrote it here for infinite, for finite.
But then you don't have a Cayley graph that's an expander for you.
Yeah, I do. This is a Cayley graph.
No, for Z, for HI.
Yeah, so.
Yeah, example.
Yeah, okay. So, yeah.
I mean, I can recall from the eigendimensional expander examples, we know of these HIs that are like these off-diagonal.
Yeah, off-diagonal things, like elementary ones.
Maybe there's easier ones to think about.
You look at in this infinite group of like SL3Z, you look these HIs are all cyclic, and they are, but then you don't have the second property. So I'm teasing a little bit, but they are cyclic. An elementary matrix is just a matrix which has ones on the diagonal and some element of diagonal. It's just what you do when with Gaussian elimination. So anyway, I want to say about how this continued, because combined with this extension of Kashdan's result, so Kashdan proved, SL3Z has property T. Kasabov and Nikolov proved it not just for Z, but for polynomial ring over Z with any number of polynomials. I'm not explaining how, but this is a very powerful thing because you can plug into these variables, even matrix algebras if you want. And then this leads to eventually this method and this result lead to a paper that basically proved what we wanted in the previous slide. Essentially, all simple non-commutative finite groups expand with some constant number of generators. So this is a fundamental understanding. In particular, you can take SL and Q, fix N, and go over all powers of Q. So you have one infinite family. You can take SL and Q, fix Q, let's say 2, and run over all N. And this is another family of expanding Cayley graphs. One that stood separately and needed this amazing result of Kasabov, like some of you know about it. Nobody knew whether the symmetric group is expanding with constant number of generators until this work. This work uses, this is an amazing combination of combinatorics and algebra. And the set of generators is finite, but very hard to understand. We'll talk later about simplification of it. But I want to say this, another thing that follows from this, actually from this result, is already the first time I know that some group which is not simple is expanding. And actually, it's pretty amazing how non-simple it is. You take this group, like SL2P, and you take a large power of it, so just direct product of this group is itself many, many times, as many as q to the n, okay? So it's it's a direct product. This still has a constant size expanding generating set. So this follows.
So R grows with Q and N.
Yeah, R goes with Q and with that, yeah. Yeah, so that's the first, and I'm obsessed with finding a characterization of all expanding groups, in particular non-simple ones. So, yeah, that's the first example.
But you're saying that this depends especially on SL and Q, it wouldn't work for other experiments?
It's maybe it works for other, but this is for SL and Q. And in fact, this result is heavily used here. The way Kasabov built this generating set is by embedding lots of SL2Ps into the symmetric group. Very episode, he mixes them in various ways. It's sort of amazing paper. Okay, we'll see a simplification, I promise you. How am I doing? Okay. I don't know how far I will get. Okay, so I want to tell you about...
Go to next week.
Yeah. Okay. Now, so we know, existence of generating sets which make groups expanding, even though they're not, but which ones? Okay. Can we take any? We know for infinite ones it doesn't matter, but for finite it matters. In particular, there was this Lubowski 1, 2, 3 questions for a long time open. What is it? It says, we know that SL2P, for example, for any P expands with this generator. Okay, that's the one. But why? Because this generates SL2Z. And we have property P. It's true also if you replace 1 with 2. Why? It doesn't generate SL2Z, but it generates a finite index subgroup of SL2Z, and then it doesn't matter. Property still gives you what you want. But if you take 3, it's not obvious, but this doesn't, the index of this group inside SL2Z is infinite. I don't know why. Well,
why? You just
why? No, you can calculate it, but you see, when you look, you see the difference between 2 and 3. Why is one finite index and the other?
If you look at SL, the second one, if you look at it as a free product of 2 groups, then you see from the theory of free products.
No, I don't see.
It's not.
Very mysterious. But anyway, if we take 3, then we don't know whether these groups expand or not. So we need new methods if we want to prove it. We can take, by the way, another element. We are working with mod P. We can take 1/2 mod P is another element, which changes code differently. But we may hope that this, are these generating, so as expander and so on. So we don't know. So what are we doing about this? We need a new method for proving expansion. And this is the arithmetic combinatorics method. So I want to tell you about this. So, and maybe just we finish the first hour. So what is this? This is, there was a movie, 5 Easy Pieces with Jack Nicholson. I don't know who remember. This will be 3 easy pieces. Not so easy, but pieces. Some of the references, really everything starts with the paper of Simonyi and Chu, who tried to find an elementary way to prove expansion. So LPS used, Delin and so on. They wanted an elementary way, and this idea starts there, and then there are many other responses, but I'll tell you how. So what are we going to do? We want to prove expansion of some G with generating set S. And as we said, we look at the random walk matrix on this group with the generators, we call it P. And what we look at, we start with the vertex, so we look at the evolution, the probability distributions on the group generated by powers of P, by applying the random walk. Now we know that, what happens if we have an eigenvalue bound, what do we do about this random walk? We know that it converges quickly to the uniform distribution because this second eigenvalue is raised to the power t when it acts on the projection of the distribution away from uniform. And this shrinks by a factor of lambda less than 1. This norm shrinks by a factor of lambda, constant lambda every time. Eventually it vanishes, it completely vanishes, and you are left with a uniform distribution. But now we want to do an opposite analysis. We don't. We want an eigenvalue bound. We are going to get it from the random walk. Turns out that this is equivalent. If you prove that the random walk converges in some logarithmic time t, this is a trace method. If it converges in some time t to something just below 1 over n, right? So the L2 square norm is just below 1 over n, then you are done. Then you have proven your eigenvalue bound. It's equivalent, it's simple calculation. So that's how we want to prove an eigenvalue bound, using the random walk on the group. Okay. So
and the 1 over n is simply because you want an L1 thing to
Yeah, we want that after you went so much down, then all norms are the same. Infinity norm, L1 norm. Yeah, you can continue and then all norms are the same. And I'm just pointing out that, this difference is really subtracting 1 over n from the norm squared of this distribution Q. I'm not sure I need it, but anyways. And obviously, sometimes I look just at the L2 norm of Q because it will be much bigger than 1 over n. I will not care about this 1 over n factor. Okay, so we want to bound this, and we bound it in 3 parts. First, we'll just get it down right. In the beginning, it's norm 1. It's concentrated on a vertex, right? We'll first reduce it to some power of n, some positive power of n. In the second phase, we'll reduce it to a power of n very close to 1, but on the other side of what we want. And in the third phase, we'll do it again and get the bound we want. So these are the 3 pieces. I'll tell you about each of them. The first phase is really, our group G will really be SL2P. That's how we think about it. It works for other, and I'll mention which you'll see, but you can think of SL2P. If you take a random walk of some constant alpha log n steps on this group, you see that you almost get a speed. Alpha is small enough, it's 0.01, right? You almost get a tree. You'll get some cycles, there will be very few of them, but it will almost be a tree. You'll see lots of elements, and you should really think of this L2 norm here as a proxy for the size of the set you are almost uniform on. So you'll be uniform on something like n to the beta vertices in your graph. That's your first step, that's your first goal. Okay.
How do you prove that? Or?
It's Schwarz-Zippel, if you want. I mean, you're generating low-degree polynomials.
No, but you're talking about which generators? Ones.
Yeah, we will pick, let's say, these elemental generators, 1, 3, 0, 1, and 0, 1. Yeah. In fact, almost any 2 groups, any 2 elements will generate the whole group we want. That's SL2P. Almost, it's, there's some exceptions, but almost.
So you write down, you have a 2x2 matrix, you write down the entries corresponding to some random walk.
Yeah.
They come out to be polynomials.
Polynomials, low degree alpha is just much less than P, right?
You see that you don't expect collision.
Yeah, you see that you hardly expect collision. And in fact, you will need something more, which I mentioned now. you need not just that you get many of them, as many more, often as many as you expect. You don't need it. I mean, even if it was a square root of what you expect would be some power. It also avoids this kind of structure. This tree avoids any subgroup of the group. It doesn't look like a subgroup, and that's also very easy. The second phase is where the arithmetic combinatorics comes in. So that's not obvious. And what arithmetic combinatorics? Early 2000, there was this amazing, very important result in arithmetic combinatorics, saying that sums and products in finite fields are orthogonal. If you have any set in the field, it's not too large, it has room to grow, right? Then it grows either under addition or under multiplication in the exponent, okay? Arithmetic progression will not go under addition, right? But multiplication will. Oh, one of them has to happen. When this happened, I was talking to Alex Lubowski a little after that, and maybe I was telling him about this. And he said, that's really interesting because when we have matrices, we multiply matrices, we combine addition and multiplication. So maybe we grow in groups. And I said, that's really interesting. And he didn't continue thinking about it as far as I know. I didn't continue thinking about it as far as I know. We missed our chance. Hefko thought about it and he proved it. So what's the statement here that actually followed but non-trivially from this arithmetic combinatoric statement? That if you have a set in your group, so now I'm specifying, I'm looking at SL2P. Later we understood more, but anyway, SL2P. For SL2P, you have a set that's not yet the whole group. If you multiply it with itself 3 times, let's say, just to avoid being in a corset, yeah. So you have to be not a subgroup, that's obvious. But if you are not, you are far away enough from a subgroup, and you have to quantify it, then you multiply 3 times, the set grows in the exponent.
It's enough that there's just not a subgroup, right? It's enough that it just generates.
It's enough that it generates, yeah. If this is a generating statistic. Anyway.
Why do you write Q is the support of Q?
Yeah, so the way I said, the way you should think about a statement like this is like you have a uniform distribution on some set. And what he proved is not about distributions, he proved about sets. And that's not good enough because we care about distribution. And here you need another tool, very basic tool from arithmetic combinatorics, very important tool, is this connection between growth in size and growth in entropy or in, to know. This is the famous Baruch-Semeredi-Gauss lemma, but Baruch and Semeredi first knew how to do it, but with the terrible bounds of the regularity lemma, and Gauss had a very beautiful proof with the polynomial bound, which were essential for all these results. So that's this another arithmetic combinatorics tool. Once you have it, you can do the same for distributions. And this is what Bourgain and Gamble did. They proved that actually this happens for distributions, so you achieve the second step. Okay. If you just convolve this distribution here with itself a constant number of times, you go from n to the beta to n to the 1 minus gamma.
So what did Sarnak and Shu do? Because they are
I'll tell you what they did. They did SL2P with specific generators, Ramanujan generators. They did something very special happens with the Ramanujan generator. The norm of, let me not get into it. Something special happens. The words are really nice. But the main thing they did is have this insight, which I'm going to talk about now. Because what do we do? Okay, we got to almost what we want. What do we do? Well, we can convolve our distribution with itself. Again, that's the only thing we do. That's a random walk. How do we pass this n threshold? So I'm going to tell you this in the next slide. I just want to mention that this was called the Bourgain Gambord machine, was taken to arbitrary groups of bounded rank, like SLD, is fixed with, over some field, and it works for all of them in this. So they developed a theory of what's called approximate groups, and have this very general result. So a very different way of proving expansion in groups in this kind of linear groups of bounded rank, which work for essentially all generators, almost all generators. So now we want to talk about the last phase. How do we get across this 1/n barrier? And how many steps do we need? Turns out we need one step. Just convolve. If you have a distribution like that, do it with itself once, and you are over the 1/n step. And that's pretty amazing, and that insight is already in Sarnakic. So this is the story of, so that's why I want to explain this last step. What we want to say, here's an upper bound which is trivial, this Cauchy-Schwarz. If you convolve two distributions with themselves and see how close they get to uniform, Cauchy-Schwarz tells you it's just most n times the product of the norms. If you don't see that, well, you can see that each element in this, each component of this distribution is bounded by one such, by Cauchy-Schwarz, and you have enough. Anyway, we'll see a proof of this actually in a second. It's very simple. The point, but it's terrible. If you have 1/n to the 1 minus gamma here and here, you are getting worse, not better. So what do we do? So we always say this, the great goal of many mathematical endeavors is to beat Cauchy-Schwarz, right? As many of you know. We beat it. So we can divide by this number, m of g. M of g is the multiplicity or the dimension of the, the smallest dimension of a non-trivial irreducible representation. When your dimension, when except for the trivial, you have only very high dimensional representations, you gain in Cauchy-Schwarz. And in these linear groups, we know all the representations. And you know that there are some power of n. So divide by the power of n, this makes sure that you can, this becomes meaningful and you get below the 1/n barrier. This insight is in Sarnakic, this multiplicity of eigenvalues. Let me prove to you this inequality. I just want to say that because people ask about the generators. For instance, to P, there is a resulting any. If you generate as expander.
Is it not for only positive?
Maybe not for all P, maybe for infinitely many P's. Yeah, you're right. Maybe for infinite. I thought there was another paper, but
It's false or it's just that?
No, we don't know. Yeah, for infinitely many. So let's go to this inequality. This time. Doing various diversions, that's diversion for quasi-random groups, which is a name coined by Tim Gowers. So he knew about Sarnakic, sure, and he defined for his purposes, for arithmetic combinatorics, let me not tell you why, this parameter of a group, M of G, again, is the minimum dimension of an irreducible representation, that's not the trivial one. Okay, and he calls the group quasi-random if this grows. In general, it grows. This has many applications that we'll not talk about. But in this paper, this inequality appears. I mean, it was sort of implicit even in Sarnakic too, but it appears explicitly. It's very elegant how to beat Cauchy-Schwarz for functions or groups. And what you need is that one of them has expectation 0. You notice that when we have the L2 norm of the distribution minus the uniform distribution, the expectation is 0. So we deal only with this kind of distribution. You want it so that you don't see trivial representation. So that's what we want to prove. And how do we prove this? Well, remember convolution. We had this inequality there. Regular representation is additive, multiplicative. One way to say this is to look just at one, that is the first column of the representation for this and for, let's say, G. Then you get them as vectors. This convolution of these two vectors is this matrix R of F still times the vector G. It's the same statement. So what do we do with this? We first do the obvious thing. We just put norms. So really, after we do this, all we need to do, if we want to prove this, is just bound the L2 norm of the operator norm squared of the regular representation of this arbitrary function f of expectation 0. And we need the bound that will divide by the multiplicity. Where does it come in? It comes in very simple. This norm is the singular value squared appears in the trace. This is most the trace of our transpose. Okay, that's a trivial inequality. So, and what is an element of the trace in this? I said every row and every column of R of F is F itself. So you get the norm of F squared, right? You get it n times if you don't know anything. But if you know something, if you know that this eigenvalue, top eigenvalue appears n times, which you do, then you can divide by it. That's it. It's an extremely powerful way to beat Cauchy-Schwarz. Okay, let me say just questions about it. This is the Urgen Gumball machine. Let me put one more slide because then in the next part we'll talk just about Zigzag. The next part is about, no, I have more.
Want to take a break?
Yeah, let's take a break. Yeah, think about it. Yeah, 5 minutes.
זה עדיין מעניין.
זה עדיין.
שלוש שעות.
לא, 50 שנה
50 שנה בשעתיים. זה הקצב הטבעי שלך.
לא, אני לא בכלל. לא, זה שקפים, שזה באמת, על הלוח באמת, אבל זה הרבה יותר.
לא, זה כתוב שזה שקפים.
How do they translate the 316?
How? The 316 theorem.
Yeah.
The 316 theorem is really that SL2P expand. Because it's
about surfaces,
it's about congruent subgroups.
Yeah, but it's about the eigenvalues of the orbifold that you get. Surface.
I'm not sure. I don't usually go
316, but it's
but the graphs are always like better than them or the other way around. I think that was the original
316 is that you take so SL2Z acts on the upper half plane. Then you get, if you quotient by this, you get some orbifold. It's not a surface, right? Two-dimensional orbifold. It's like a surface with some points that are behaving.
Right.
Look at all
You look at the eigenvalues.
No, you look at all subgroups of SL2Z.
Which?
No, modular.
Yeah. Which when you mod by B, they map to the identity. So it's all the kernel of the map. If you take a matrix mod P and you see the identity, take the kernel of this map. This is a subgroup of SL2Z, and like these are the subgroups that like you look at their action on the upper half plane and you mod out by this. Get bigger and bigger surfaces because these are smaller and smaller subgroups. And somehow the eigenvalue of all these, so this is like a family of Riemannian manifolds. There is a bound on the Laplacian, like the spectral gap of all these surfaces uniformly. And the bound is 366. It's conjectured to be 1/4.
They are conjectured to be Ramanujan surfaces, but it's only known that they're
360. 1/4 will be the Ramanujan.
And is there a way to
Now you draw.
code what it means to be a lower bound on the Laplacian surface in terms of?
Yeah, you take a net. You put
In terms of just the group that you quotient by?
It's a really nice one.
Say again.
You have a group of SL2P. You took the upper half plane, you quotiented by this group, by SL2P.
The action.
Right?
yeah.
You know what I'm saying?
No, so it's not at all
It's not
obvious. That's why
clear.
I'm surprised. No, now there is a machinery. If you know strong convergence, you know much more about the subgroup. Then
What
you
does
can.
that
There is a very naive way of at least getting out of these surfaces an expander graph. You're only caring about doing an expander.
That's not what I'm always saying.
Okay, look, okay.
Yeah, there's a number, it's 3/16, right?
Right.
So what is this number?
It's a mostly group.
Like, what is not, it's the spectral graph of the Laplacian, but
I have a surface with.
of the surface of a continuous thing,
I
yeah.
don't know what that is. I mean, okay, you can tell me you take the second the Laplacian and it involves the second derivative and blah, 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 but I'm asking. So which code out of that, what it means for the group SL2P?
Yeah, that's a good question. That I'm not sure. Like, I probably yes, because that's what they
Yeah,
do.
they use it somehow. But I did.
I don't know. I'm not
In
sure.
LPS, that's
But
what
this is in the original LPS.
So at least the way Alex described it always.
They don't-
is that
Alex never-
Before they did the Ramanujan,
He always cares about the
you
second.
can take
Or
these
the both.
surfaces
Get something out of it.
discretize them and get out of the Laplacian of the surface some knowledge about.
But that already Margulis didn't.
Exactly, and they weren't able to beat, so they beat somehow Margulis that way, but they weren't able to beat, they called Cayley and they asked him whether they beat the best eigenvalues this way, and they didn't. Then they worked harder with the actual Ramanujan, but they already gained something non-trivial that I think is better than Margulis only by like some discretization using 75% more. But again, I don't remember how it was. As you said.
Okay.
So tough.
Yeah, super tough.
Yeah, it's a good question. Anyway, let me go back to this question. So, thinking back like 30 years ago, we knew expanders, but we didn't know whether expansion is the property of the group or also of the group of set of generators. I told you that if we talk about infinite groups, any generating set is good enough, but we are talking about finite groups. And we saw that in these linear groups, essentially every set we take. We don't know that, but we think that. So it doesn't depend on the generating set. For abelian groups, also, it doesn't depend. They never expand with a constant number of generators. And this paper, which is a beautiful paper and influenced me a lot, it has lots of gems. We may go back to it. They ask whether there is a group which is schizophrenic, which can be expanding or non-expanding depending on which constant side generating set you take. And this got us to collaborate also with Noga Alon, and we found such a group. I'll tell you about this group in a second. This is some called semi-direct products of two groups, which I'll talk about a little later. The real obvious answer should have been the symmetric group. Of course, we know it cannot be expanding. For example, if you take transposition and a long cycle,
I mean, it can be
non-expanding. If you take these two generators, one transposition, one Hamiltonian cycle, it's not expanding with this generating set. But nobody knew that there is a generating set until Casabo. So, so he supplied this a little later, he came up with this, so who that this is. Schizophrenic, I promised to tell you that finally we have really simple expanding generating set for the symmetric group. I just discovered it a few months ago, this paper. I'll tell you what it is. So if you think of n, this specific n is you request fp cube, except the zero element, and you have the following permutations. So these are your elements, your symmetric group over n. XYZ is sent to this very simple generator. You cyclically shift, or you add x to the second, y to the first component, or you add y squared to the first component. Degree 6 graph on the symmetric group, it's expand. It's pretty amazing, and we'll talk about it even more. Yeah, we'll talk about this, where it comes from in the next slide. But I want to tell you about this. Yeah, I'll tell you about this the following slide. So I just want the last one on the mother group approach, a very different one. Yeah.
So you look expanding and non-expanding, but there's stuff in the middle, right? You can have.
Oh, I'm thinking about a fixed family.
Oh, we can have a fixed family, maybe with different types of growth in intermediate. I mean,
Yeah.
more than two types of.
Yeah, you can. No, but yeah, you're right. Yeah, you can have finite, but yeah.
What do you mean two types of growth?
And there's the exponential growth where you start with a constant and it grows like exponentially fast.
Let's delay this final point. I want to tell you about the last method in which you have this mother group approach.
I'm trying to slow you down.
Yeah, but not about things I want to talk about. Really, another very ingenious way of getting expansion is this random group method. So what's a random group, especially a random infinite group? Comes back to the genius of Gromov. So what did Gromov talk about? He was at the time interested in hyperbolic groups, and people had all sorts of conjectures that many people worked on. He was looking for more examples of hyperbolic groups. We have them from arithmetic lattices, from, surface groups. He wanted many more groups that are different, and he made them in this random way. So this is what's called a group presentation. You take a bunch of generators, symbols, any symbols, let's say, and you take a bunch of relations. Relations are simply words in the generator. In this slide, I'm talking only about relations of length 3. So words of length 3. And what is the group? The group is the free group generated by this element, smalled out by these relations. These relations are identities. And you pick the relations that's random. So what happens? The question is, how many? There are m relations. How many relations should you pick to get something interesting? You pick too many. More than quadratic relations, you have cubic many or something. More than quadratic, then the group becomes trivial. There's too many conditions. Okay, it's very easy. See, that's trivial also. This is the main theorem in this paper. If you pick slightly below quadratic, then you get an infinite group. So you get a real group, and it's hyperbolic with very high probability. And this idea of this random group model and expansion was connected by Zhuk, who also said that there's another thing you can do. You can take now at least n to the 1 plus epsilon generators. In fact, n log n will suffice. And then you get property T. So you have many random examples of groups with property T. Of course, nobody guarantees you that they have any finite quotients, but you can at least get property T. And you can get hyperbolic groups with property T because there's plenty of room here. Why does this have property T? For those who attended the many high-dimensional expander talks, you know how to do it. All you need to do is to prove that the link is an expander.
then you need the M to be 3.
No, not the M,
Length
the
of
length.
the-
Yeah, I know. So but that's why I'm specifying. You can do more. I'm just, in fact, in Zuck's paper, it's only relation to what is the link? You have these triangles, right? These words that go to the identity. So if you look at the links, the neighbors of a vertex, they look like a random graph. What's the degree of the random graph? It's just n to the epsilon. Or in fact, bigger than log n Mustafa. Random graph is an expander, the link is an expander. And then you have this powerful local to global method. If your link is an expander, then you have expansion overall. In the infinite groups, you get property T by Garland. One obvious question that I was wondering since I saw this paper, which is more than 20 years ago, is can you de-randomize? Anybody knows? It was solved. Yeah, there are explicit ones.
Explicit
Right.
what?
Explicit relation that have this property.
That have, what, I mean, you can just build an
You
expander graph.
guarantee that it's an infinite hyperbolic
So how
graph.
do you know that it will be an infinite group? You can put whatever you like.
You need to guarantee that the group doesn't
Yeah,
disappear.
that's trivial.
Can you
Yeah.
also make sure it has finite quotients?
Yeah, very good question. Yeah, the paper I told you about has infinitely many alternating group quotients. Now I wonder, the obvious thing
Like
is,
the Kaplaska sub of is a random group?
no, it's a deterministic, it's only this group, the triangle groups,
Wait, I don't understand the last row in this slide.
the last row.
Yeah.
In this paper, they take these groups or variants of this group.
Which
There
are
are groups of
deterministic.
deterministic,
Uh-huh.
yeah. And the quotients are quotients of these groups, which give you, expansion with these generators, because these are the generators. I mean, the generators of the previous slide, the simple linear maps on X, Y, Z. The
Oh,
generator.
these were generators of the alternating group.
Yes, yes, and these alternating groups appear in the as quotients of this group.
Of these infinite.
Yeah, now I must say, I don't understand this paper. I don't even, it's not even clear to me that the relations are of length 3 here. But the combination of this gives you the simple generators of.
So does this also give you like a 2-dimensional?
Yeah, so that's my question. I need to understand this paper. So I started looking at it again, and I looked at it a few months ago now for this talk. I started looking, I need some volunteer, like Doron or Michael.
There were already like many other applications of this result. Like I saw several,
Yeah,
like this was already used many times.
the first one.
No,
The
second
last one, yeah.
Somehow, yeah, it's very
But
fun.
not for HDX, right?
No, for things in
Yeah,
group
that's what
theory,
my-
understanding
yeah,
something.
that's extremely interesting, and I wonder whether we have new HDXs from this. I don't know. Okay. Good. So yeah, I don't know how much I'll have time to do, but I won't tell you about the last method. It's my favorite. But I thought, I don't know, it was done 20 years ago. I thought maybe I should prove the Zigzag theorem. So I will. So we introduced the Zigzag graph product. What it tells with high level is if you take the appropriate product of two expander graphs, you get a larger graph, which is also an expander. And this can be iterated, maintaining fixed degree and expansion. And that's a combinatorial way of getting a sequence of expanders in an elementary proof. So avoiding all this was a major, thing that made me happy at the time, that we avoided algebra. But we'll get back to algebra. First, let's talk about this graph theoretic side. So what's the construction, if you didn't see? Here's two graphs. So this is the number of vertices, the degree, and the bound of the second eigenvalue. Okay? So you have two graphs here of this is big and this is small. This is not just big, maybe the degree is big, it's not constant even. We don't care. However, the degree here is the number of vertices there, which begs to put copies of H around every vertex of G. Right? And that's what we do. Suppose this is H. And we define the zigzag product as follows. So the vertices are just Cartesian products. Right? We put a copy around every vertex of G. G is blue and this is yellow, orange. Now, if we leave all the edges of both G and H, this is called the replacement product, which I mentioned before. This is already good, but not as good as zigzag product. What zigzag product does is erases all the edges and instead of them put zigzag edges. So connecting this vertex by small step in the cloud, this is called the cloud of H around the vertex, then switching to the opposite side of this edge. It's a deterministic step. And then take a random walk on the other cloud. And you forget about all these edges and just put this right in all possible ways. Okay, that's a zigzag code.
But you did explain how to embed.
Any embedding is good, very good. At this point, doesn't matter how you embed the edges. All of them will work. Later we'll talk about this. Yeah, now it doesn't matter. So zigzag is any way you do. Okay. And the zigzag theorem says that if you have these properties, both of them are expanders, then you get a graph with degree. So it goes, it's the product, right? N times M. The degree is just d squared, just the square of the small graph degree, right? Because only here you have d possibilities and here you have d possibilities. This is a unique, you just go to the other side of that. So,
Wait, the expansion parameter is.
and the expansion, sorry, thank you. And the expansion parameter adds up. So if these are small enough, which you arrange, then you.
But for iteration, it's not good.
Yeah, I'll show you how to do the iteration. Yeah. So that's one step of zigzag. So you can reduce the degree of the big graph doesn't matter. It's amazing.
So this is the second eigenvalue of the unnormalized adjacency matrix.
That's the random walk matrix, yeah.
Or random walk matrix.
Yeah, random walk matrix.
What do you mean if? But this doesn't give you if and only if.
Then it's getting
to be a spectral graph to be small enough, no? Or
yeah, it's a bound, and if it's meaningful if alpha and beta are small. And let's see why it's useful. Okay. Here's the proof. Okay, I promise you a proof. So I already proved in the introduction of the paper. My course didn't like it very much. It's about entropy waves, but that's my way of understanding what happened. And this is really how we arrived at it in the beginning, because we were thinking about extractors and not about expanders.
Really, it's in the title of the paper, entropy waves.
Yeah, of course. Yeah, I was a senior course and I could force them. They were postdocs. I'm sure you'll sympathize. Okay. Yeah, so what is information theoretic? So first, let me tell you what is an expander, the way I think about it. Expander is any graph where when you take a random step, you get an entropy boost in your probability distribution. So if we are here in the graph, here are two distributions. P is before we took the random step, and P prime is after we took a random step. So what do we do in one step? We sample from P, we have some vertex, and then we take a random walk to a random neighbor. And that's our new distribution, P prime. And I want to say an expander high level. I mean, this is how I always think about expanders. You added now log D random bits, right? You went to a random neighbor. You should gain something in entropy. If you do, that's an expander. So entropy is right now undefined. It's whatever you feel is entropy. If the entropy is not full, you are not yet uniform. You want to gain. And this is what it is. It's an expander if you gain some constant in the entropy, maybe related to log D. And You could, and it's used, this way of thinking is useful because you can think of entropy as the size, log the size of your set that gives you vertex expansion. You can think of the entropy 1, external entropy, and this gives you the, what do you call it, expansion in entropy. Instead of the Poincaré inequality, and if we take L2 norm, then we log L2 norm, then we are talking about the normalized spectral value. So it's very convenient to think about it this way. So now let's see the proof of the zigzag theorem. So you want to prove that this zigzag, adds entropy. What's the zigzag? We want to go to a random neighbor, switch to the other side of the edge, VB, and we go to some UC, and then we go to UD, which is the last endpoint of this edge, zigzag edge. So we want to show that adds entropy, and there are really two random steps, and you want to say that one of them adds entropy. H is an expander. The only way it will not add entropy if it's all uniform. Right? So there are two cases. We want to show that this increases in entropy by some constant. It's all high level, but it captures the whole proof. If this entropy in the cloud, the condition where you are, is not full, then you already made it. It's a random step, adds entropy, and fine, you are done. And later entropy will never decrease. Entropy doesn't decrease. So that's case one, which is easy. But it should be case two. If you don't win in the first, you win in the second. It's a win-win. Why does it work? Because, so let's assume now that the clouds are uniform, those that we care about. I mean, it's all conditions on V. It is uniform. So you didn't get a single thing in the first one. It was total waste. The next step is deterministic. But it's deterministic, but if you think that you were uniform in V, then when you look just at the big graph, the graph of G, you really took a honest to go the random step on G. And this should add entropy. This entropy, this is a deterministic step. It adds entropy only when we project on G, but we don't. We live in the big graph. So what it means is that the entropy of this pair increased. But if the entropy of the pair increased and the entropy of the first component increased, means that the entropy is a deterministic step. The conditional entropy on U decreased. Now it's below log n, and this random step will gain entropy. This is how that thing to it. Now so this is written here.
So you only need the third step for symmetry.
Yeah, it's really symmetric. The argument is not symmetric, but the
So you use only the first two steps in the argument.
No, I use all steps. I use all steps. I use expansion in both graphs. But the way I use the expansion in G was to say that if I project only on G, I get an increase in entropy. So I get an increase of entropy if I look just at the first component. But I have the pair. If one component increased in entropy, the conditional entropy in the other went down because the sum is the same. It's a deterministic step. It cannot be full. So there's room to grow in the second zigzag step. Of course, you wonder why should be the far from log m or not log m. You don't do it in, you do it in, why are these cases mutually exclusive? Because you do it in linear algebra and then you have the perpendicular and the parallel. And that works beautifully in as many lines, alphabet. So that's the proof. Okay, so I want to give the proof.
Wait, but so what did your postdocs not like about it? They don't think this was the right intuition, or?
Well, the linear algebra gives it all. Why do you waste words on entropy waves?
I mean, this is a proof sketch. When you write down the actual proof, it's just linear algebra.
Yeah. So, but anyway, I like it.
So Avi, this is the whatever entropy 2 version of the argument.
Yeah.
Do you also get like analogs of entropy 0?
This is how I mentioned. This is how we get the lossless expander. We do it actually in mean entropy or proximity to mean entropy. Yeah. Yeah. So here's the iterative construction for those who don't want. So you start with these parameters and you want to iterate. So we have this Zigzag theorem, and now we want to iterate. How do we iterate? We start with some fixed size expander with this parameter. So you want d to the fourth vertices, degree d, and bound a quarter on the eigenvalue. You can do it. I mean, if I told you that, I mean, like the degrees, fourth root of the size of the graph, if I told you square root, you tell me projective plane. It's like a square root of the project. It's no problem. It's a very explicit, simple. Even a random construction would do, but there's a very simple explicit construction of this graph. And this is how you iterate. The first graph in the sequence is the square of this. Okay, I want a sequence of graphs all of degree d squared. Okay, so the first one would be just the square of
Square, zigzag square, you mean?
no, normal square. I squared the adjacent dimension. I squared the adjacent.
Yeah, walks of length.
Yeah, walks of length. Yeah, square. And what happens in general? In general, if I have gk, I'll square it, so it will be of degree d squared. I'll square it, and I'll zigzag it with 8. So let's see the parameter.
The squaring brings like the
Yeah, it's written. Yeah. So I claim that they are all, growing sequence of degree d squared and parameter 1/2, all of them. Okay. Why? Because inductively, we have this property for gk. When we square it, we square the degree and we square the eigenvalue. So we are down to quarter. And we have d to the fourth, which is exactly the size of h. We do zigzag, and we go back to d squared and half a quarter plus 12. Some of you may not like it because this is not strongly explicit. It works in polynomial time. Yeah, like me, yeah.
No, I also don't.
Yeah. I'm sure I have a minion. It's polynomial time in n to construct an expander of size n, but it's very easy to remedy. All you need is to add here a tensor product. The tensor product of the graph with itself, grows quadratically and essentially maintain the eigenvalue. So you mix it in these steps and everything was fine, you get exponentially long.
So any way to avoid the self loops?
There are self loops, there are many cycles of length, 4 in this graph. Yeah, no problem.
Why do you want to?
No, I mean, you have an eigenvalue bound. I mean, you have an eigenvalue bound.
I mean, can't you just erase them?
Will erasing preserve the spectral gap? Maybe. Oh, you're saying I might just affect the lambda n, lambda 2.
Always, like if you erase them, you're always better off.
Except, I mean, I might kill the lambda n. Like I might make the graph bipartite.
Yeah, you don't. Yeah.
Oh, okay.
But I don't care about it. I like self. I would add self loops to any graph. So there are many consequences. I want to talk about some of them that's related to this, but I mentioned there are these lossless expanders when you work with mean entropy in the same spirit. And of course, so you want vertex expanders that expand really by the degree.
25.
What?
It's 25, not 05.
Yes, 25, sorry.
Some of the authors would be
So
like
finally,
6.
there is a simpler.
I was just thinking about it. They were all born, I think.
They were all born in.
That's all I can say.
Yeah.
Well, one of them certainly was born.
That is my age. So lossless expanders came out of this. The connection that I'm going to tell about with semi-direct positive groups is coming next. It leads to new non-simple groups that are expanding. That's what I hope to explain, really. And Omer Reingold's result as its influence on Rich and the PCP theorem You all know about this. So the super expanders, an amazing paper of Mendel and now, I'll not explain it, I'll just say one word. Super expanders can be defined by a Poincaré inequality. It's, it's just another way of writing the eigenvalue bound. And it works with L2 nodes. You can ask about LP node. You can ask about any node or any sufficiently round node. And you wonder whether this inequality works with other nodes. Turns out that if you just care about LP nodes, Matuszek has a proof that any expander in L2 is an expander in any LP, any finite LP. But you want in any norm or any sufficiently round norm, if you get it, maybe every expander has this property, we don't know. But that's a question in this paper. It turns out that Lafort, using heavy algebraic machinery, was able to construct them. And Manor and Mendel managed to construct them using Zigzag. It's a beautiful paper. It's called nonlinear spectral gap. It's a beautiful paper. More consequences of Zigzag is, of course, I'm sure some of you know about Amnon Tashman's graphs, codes that nearly meet the GV bound. And a consequence of this, which I may mention, making all groups essentially Ramanujan, which is very surprising, even though it's just Tashman's result. And there's something beautiful for property testing, which let me know, you can ask me about. Let me not tell you. So this new proof of expansion turns out to have lots of implications that don't follow from any other way of constructing expanders and have nothing to do with expanders, some of them. So what's the relation with semi-direct product? And what is semi-direct? So remember we proved that this particular group is schizophrenic. That was our motivation at the time. It's a way to phrase the zigzag theorem in group language. That's what we really did in this paper. And here's the statement. Take two groups, G and H, and suppose G acts on H. Okay, that's the natural action. Assume that, so now I want to tell you a group theoretic version of the zigzag theorem. So what do you need? You need, first of all, the G itself expands. So G is you think maybe G now is a small group, acts on a big group, H. G expands, so somehow G is H in the previous picture, I probably switched that. And anyway, G acts on H. Suppose that G is an expander with a constant generating set, and H is also an expander, but now you don't need the degree to be small, like in Zigzag. But what you do want from the set of generators is that this is a constant number of orbits under the action of G. So you take a constant number of elements and apply the action of G to all of them. And all you need is that this is an expander under this maybe bigger generator. I'll have an example in a second. But then what happens, and here comes the embedding of now we want to put copies of G and the H vertices, but the zigzag product of these two Cayley graphs is the same when you embed the H's appropriately as the Cayley graph of this new group, the semi-direct product of G and H, with this generating set. You forget about the orbits, they just take a representative from each orbit. This corresponds to this deterministic step in zigzag. And because of the zigzag theorem, you get an expansion with a constant number of generating sets now for a Cayley graph. So you can do zigzag for Cayley graphs and each arrays, as we'll see, and remain with Cayley graphs.
But what's the size now?
Everything is the same parameters as this. So I just want to stress this point that now the embedding method, you have to embed it so it will fit with semi-direct product. What's semi-direct product? It's like direct product with a twist. Maybe I will not define it. I just want to talk about this action, just that you're a very example very related to the schizophrenic group. Let's just look at the cyclic group acting on the Boolean cube by permuting cyclically shifting the coordinate. So here I want to tell you how does this schizophrenic group look like. I mean, you should replace Cn with SL2P, which contains Cn, Cp, in order so that this group will be expanding. But anyway, just look at the cyclic action. If you, what is the orbit of a single unit vector? You cyclically shift it, you get all the unit vectors, right? So you get the Boolean cube. We know the Boolean cube is not expanding. But if we take two elements, let's say it's random, and look at their cyclic shift, then you do get expansion. How do we know that? We know, I mean, in coding theoretic language, it says that two random orbits like this are give you a good code. And it's a union Chernow bound and union bound. It's very simple. These are two n elements. We know that if we pick them two vectors that's random, they'll generate the cube as an expander. You don't need to pick them as random. You just need to pick two and they're cyclic. This for prime. Yeah. And it's a great open question that I love. It's to find. We don't know if this. Yeah.
But if you take random elements in F2N, you take the orbit, not your orbit.
No.
So it's only orbit.
And in fact, you need just one, right? Because you can take one, U or V can be E1. You can change base. Anyway, we don't know a vector that would do it, that its orbit will generate, expand. Yeah.
That's still encoding or, right? Like I should think of it as like.
We don't know such an explicit code. We know it's.
I don't know, but I'm confused for a moment about the relation to codes. Like this is a good expander if the encoding induced by V and U and their cyclic map. Like how do you?
We saw before
in
when I talked about the Fourier transform, I said that the bound of the Fourier coefficient is the bound on the eigenvalue because this was diagonal.
Right.
It's the same. So this is our correlations with parity of the characters. That's what bound.
The rules of a matrix is give you a good code, and they're expanding generators for them.
Yeah, it's the same. It's the same statement. You get more than distance. You get that every word is, has weight.
Yeah, my confusion was that it's the rows that are expanding, but the encoding is the columns.
Yeah, encoding is.
I'm always confused by this. Yeah.
Oh, yeah, but it's okay. So I want to, maybe the last 10 minutes, I want to tell you about how to build non-simple groups that expand with constant or almost constant generating setting, two setting. I'll do it a little fast, but so what is the commutator subgroup of a group? This is just taking all pairs of commutators. Their collection is a group. And you can look at what's called the central series. You can just take a sequence of groups where each successive one is a commutator subgroup of the other. If this iteration lets you, finalize in the trivial group, then you call this group solvable. And the number of steps it takes is called K. Okay? That's a very fundamental. Solvable groups are groups that are close to a billion. The smaller K is, they are close to a billion. If K is 1, they are a billion. Okay? Now, it's a beautiful, it's the same paper I mentioned before, Flubotsky and Weiss. They show the following. We all know that a billion groups require logarithmic number of generators to be expanding. They generalize it. They say that if you have a k-step solvable groups, you need a number of logs, which is the length of k. And it's a beautiful book, just beautiful. I'm not saying anything about it. Yeah, so how close to the truth is this? So it's extremely close to the truth. In this paper of Meshulam, we show that, basically the same number of iterations of log you can get expansion. So their result is typed essentially. I want to tell you something
This is
about
random,
this.
like how do you do?
What?
This is random, how do you measure?
I'll tell you.
Ah,
I'm telling you this work with Meshulam in 2 slides. So this near constant degree, but the soluble groups cannot be constant. It will be log star. And what we are going to iterate now is the following. We have already an expanding group. We take its group algebra with a finite field, FQ. So it's the first time I'm using not the complex numbers, but FQ. So Q has to be relatively prime. The size of the group. Of course, the group acts on the group algebra, just like the cyclic shift on. Yeah. We start with any constant size group, doesn't matter. And the sequence will iterate this again and again. And so the growth, as you see, because the group algebra is exponential in the size of the group, the groups will go exponentially. On the other hand, we'll find generating sets which go only polynomially. And because of this, we get this log star.
But what do you mean that? The group algebra is not a group, or you're talking about?
No, the
With
group
addition.
algebra is an abelian group. What do you mean?
addition, just the
It's
addition.
an abelian group.
What do you mean the semi-direct product?
The semi-direct, because the group acts on the group algebra
Yeah.
by left multiplication.
Yeah.
So you have an action, and now you look at orbits, like the cyclic shifts. Like the cyclic group acts on its group algebra, which is just a Boolean cube.
But what is G prime? What kind of object is it?
It's a group. It's a semi-direct product of G and
The elements are pairs,
Once
the
you
element
have-
of G,
yeah.
the polynomial
Once you
of
have-
G. Like,
I didn't define semi-direct product, but once you have an action, you have a semi-direct product. You have an action. G acts on the group algebra. But what's not clear?
Usually, so semi-direct product, you have two groups, not a group and algebra.
No,
It's a group.
the algebra.
It's an abelian group. Forget the algebra. I
just the
don't need
addition,
that.
just the addition of
Addition.
the G.
Yeah, it's an abelian group. All I want that.
Okay, that's a binary group.
Yes, abelian. So it needs, but all it needs is to expand using orbits, right? So that's okay. Okay. So we'll assume, I mean, we prove that these are all expanding, and we'll see that by definition, really by definition, will be K-step solvable. So how does it work, and what do we need? What is the essential ingredient? We want to maintain some invariant, like expansion. So we have G acting on the group algebra, which is a vector space, just a abelian group. What we want is to maintain the expansion. So we want that after one iteration, it's still expanding, and we want control on the side of the generating set. So what it turns out, right? So all we need is to prove that this abelian group expands with constantly many orbits. It looks very much like what we saw with the Boolean cube. We want this, and it turns out that this is not so easy to prove. In order to prove it, you really need a control. I mean, you really don't want to diagonalize the group algebra and work on the matrix algebra, full matrix algebras, where you understand the ranks of matrices and how many there are. And you need this control, and it turns out that you get this control relatively simply if you have the following. So we wanted a property of the group algebra, we want to derive it from a property of the group. And the property of the group we need is that the number of small dimensional representation doesn't grow too much. It grows at most exponentially. For each D, you want a small exponential in D.
How do you use that?
Well, this implies a control. I mean, now you have this small matrix algebra. For each one, you count how many are of each rank, and you add them up. It's accounting. This is how you use it. So that's what you want. Very nice. You want it, and you hope that it will follow from expansion. It doesn't, to the best of my knowledge. I'll tell you in the next slide something about it. It doesn't follow from expansion, as far as I know. But if you add another condition, the group is monomial. This technical condition basically says that the irreducible representations are all induced from characters of subgroups. Doesn't matter. Some property. Then you have it. So you almost maintain an invariant. What you want to keep it an invariant is a theorem like that. If your group was monomial, then the semi-direct product with the group algebra is also monomial. And then you have an invariant, you can iterate it as much as you like. So I want to talk about this second part, this theorem too. Suppose, this is a really great question. Is it sufficient to have an expanding group so that you will not have a fast growth of the, like in a billion group, all the representations are one-dimensional. That's terrible, right? And it doesn't have this property. So this is a conjecture. It's true in a billion groups, of course. It's true also for simple non-abelian groups, because their representations are, the worst is a symmetric group, but the first representation is what's called the standard representation. Dimension n, it's not squared, 2 to the n is not squared the size of the group, but there is only one such. The next one is n squared. So you are fine even for the symmetric group. And for this example I gave you before, this conjecture is tight. You get exactly exponentially many representations of some dimension, p in this case. So I believe this conjecture. You want to prove it? Let me tell you what's known.
Sorry, G is expanding, we already learned, is not a group property.
Yeah, but I want to say that if it expands with any constant generating set, yeah. I believe that. We tried pretty hard and we tried over the years. But something a little weaker is known and it's simple. So there is a connection to expansion. It's just that the growth is a little worse than we want if you allow this square. It's basically a volume argument uses expansion in a very basic and simple way. So that's what we know about. Yeah.
Could it be driven in in the other direction in some way? Oh.
Okay.
Amazing audience after 2 hours.
But for the last group, it doesn't generate with any set of generators. So
No, but with some. Yeah. It's a great question, and I'm wondering whether this characterization of expanding groups would be amazing.
And it's also it's for D up to like log size.
Of course, yeah, you don't care about the above log, you don't care, yeah. Of course.
So for solvable groups, you know that you don't have this one.
What?
I mean, solvable groups are not expanding, so I'm asking if
they are not expanding. So
you know that you'll have the
yeah. I think it's all the examples I know it. I want to just the last slide tell you about a non-simple group where you can expand with a constant number of generating sets using Zigzag. And this is this paper with I mentioned before, with the inertia level and Eyal Rosenman. So this is a tree. I want to tell you what the group is. This is a tree of depth k and degree d. And the group is the automorphism group of this tree. What's the automorphism? You around every vertex you can permute the children. Okay, this is the automorphism group of the tree. This group will be expanding, but I have to augment it because this group, if you allow all permutations, you allow in particular, you really want even permutations. Because symmetric group has this subgroup of degree 2, which is bad. If you iterate it many times, you have an abelian group, a Boolean cube, and that's very bad as a quotient. Expanded groups cannot have that. So I want to allow only even permutations of the children. Okay, and this is a group that will expand. It's a very simple group. So this is how it looks like. Each vertex has a permutation which is even on the children. And composition, your group product is you do it vertex. And for any k, fixed d, for any k, this expanding group is an explicit, real. So this, here it is. By the way, as you move from k to k plus 1, this is really adding a vertex at the top and having d copies of the previous group. And this is actually a semi-direct product of a special type called the risk product, but I don't have to define it because you really know what the group is. And we prove that for this infinite sequence of groups, for any k, you have an explicit generating set. In fact, we have a polynomial time algorithm for generating for every k. And I'm not going to explain this, but it uses all sorts of things, including zigzag. But one essential ingredient is a very simple version of it is the following thing. If you have an expanding group, in fact, expanding group like the alternating group, which is the perfect group, namely every element is a commutator, then you have the following, more or less. You take a direct product of the same group, and the generating set is very correlated. You take S in one coordinate and S inverse in the other. Okay, very correlated walk on this product of G with itself. And this is already expanding. And that's really bizarre because if I took SS, it will not even be connected. Somehow they decorrelate very quickly.
So you can take S to be involution, and then S inverse is the same as S.
No, you cannot. Then
Because the group is perfect, then
there are no involutions. Yeah. And I'm cheating a bit, but basically this is, so that's a very surprising fact. A much more elaborate thing is needed to actually prove this. So let me skip this. Let me just. I want to just say something about Ramanujan graph. You all know the Ramanujan bound, our famous Ramanujan expander, but they are for very specific groups. And the result, it also follows from Zigzag, and actually I mentioned from Amnon Tashman's result, is that any group you can find generators that are almost Ramanujan. So this is a theorem in this paper from a couple of years ago. You can start with any expander on this group, just that it's expanding. And you can take words in the generator, very specific words, to make it expand with almost 1 over square root down. Doesn't matter what the group is, very surprising. It seems that Ramanujan is a very, but you can guess it, and this really follows by really the transformation from Fourier transform to irreducible representation. Fourier transform, you have parity, like over the cube. And for arbitrary groups, you take L2 norm of the representation. That's all we do to get from here to here. Almost. Anyway, let me stop and ask questions.
Okay, now it's time for all the questions.
So could all groups be actually Ramanujan in this sense?
I don't think so.
Do we know that?
I don't know, but I don't think.
What all the questions say?
Whether you can really be Ramanujan, not almost Ramanujan. I don't think. Maybe we won't show this question. I'm flying to Toronto. I mean, I'll come to lunch.
Okay, so maybe.
Ask me at lunch and we'll.
All right.
I'll be
Thank you
here
very
after.
much.